Okay. Let's continue with the last part of the course. And this time we talk about a way to implement a whole body controller considering the full dynamics of the robot and in an optimization fashion. We call the QP-based task-based inverse dynamics. Why we want to use the full floating base? Because if we have the full knowledge of the robot dynamics, we can compensate for all the inertial effects. You remember the inertial effect we compensated for when we implemented inverse dynamics for fixed-base robot. The same way, I make a simplified representation of the robot, it's represented by the model with all the inertial properties, allows us to, from one side, predict the future behavior if you use it on optimization, but also guarantee the constraint satisfaction, because these robots, they don't have infinite actuation bandwidth, they don't have infinite actuation torque, they don't have infinite joint range. So all this limitation needs to be taken into account in a controller, in the controller that wants to be feasible, wants to create, be able to track a trajectory and still satisfy the limitation, consider the limitation of the robot. This model-based approach allows us to, if we use in optimization, to generalize the motion, because we considering all these limitations, being able to predict, we can generate different motions, even motions that are cutting the limits, that are close to the limits, exploiting as much as possible all the capability of the robot. On the other hand, whenever we use a pure model-based approach, it's always too good to have also a feedback controller running in parallel. I will comment quickly about this afterwards to correct inaccuracies and some situations. But for now, let's think about a pure model-based controller. So we recall that inverse dynamics has the goal to find the set of torques such that the joint motion follow a desired trajectory, or if we do it, formulate it at the operational space, at the task space level, we want some Cartesian position following a desired trajectory. And if we remember, we can define an attractor with a feed-forward term, let's say, at the joint level, invert the dynamics and compute the torques. And in the case of operational space case, we do the same. We have the PD plus feed-forward at the operational space at the let's say at the point in the operational space we want to control. We invert the dynamics with the bias terms and the inertial matrix reflected at the Cartesian point we want to control, and we have an additional step to map to torque. And we achieve a nice tracking of the desired trajectory because we compensate for the inertial coupling. But all these approaches, they don't have any knowledge of the feasibility constraints, like actuation constraints, for example. And therefore, we want to use optimization because it allows us to incorporate these feasibility constraints. And this is a quick introduction on the taxonomy of different kind of optimization problem you can find in robotics. There are some, the simplest one is the linear programs that have characterized by a linear cost function and linear inequality constraints. Then you have the quadratic programs that have as requires to have a convex quadratic cost, like this, with a quadratic term and a linear term, with the G matrix positive definite, and they allow to encode the linear equality and inequality as well. Then we have the least square programs that are a special case of a QP that have the cost expressed as a true norm of a linear function that has this shape. So whenever you have a QP with this, it's a least square program with this kind of costs, and also low linear inequality equality. Finally, why we are interested in, we nominated this because there are also the nonlinear programs, but the QP and LP are very fast to be solved. First, they are convex, so they have a global solution or a unique solution, and they can be very quickly solved with off-the-shelf solvers, and therefore they are useful for controllers where we need very high frequency reaction. So if we reformulate the previous inverse dynamics at the joint space as an optimization problem, we have that in the norm, in the cost, in the true norm of the cost, we have the acceleration and the desired acceleration. Okay, because you want to minimize this error with respect to the reference acceleration. Where in a reference we have all the PDE plus V4 term, so this is not really an desired acceleration. It's like a controller written at the acceleration level. As optimization variable, we have the torques and the accelerations, and as constraints we are the dynamics.
And for H, that depends on Q and Q dot. How can I?
So the optimization variables are tau and Q dot, but this doesn't mean that you cannot measure stuff. So you optimize for the acceleration and torques, but at each loop you measure all the states Q, all the velocity Q dot, and compute all the terms that you need to solve the problem.
I measure, I don't integrate from Q double dot.
No.
Measure.
No, you measure. Because in inverse dynamics, you remember, we measure, Q desired, we provide a desired acceleration, the actual state, position and velocity, and we compute torque. So it's only the acceleration that it's the desired one, but the state is provided.
And are they coherent? I mean, if I am finding the Q double dot, I'm deciding from outside Q double dot, are they coherent with the Q and Q dot that I'm...
Good question. But you remember whenever we inverted the dynamics, inverse dynamics, the first lecture, the state feedback that it's dependent on Q and Q dot serves to linearize the system. Then you get a system which is like a unit mass double integrator, like a double integrator. So depends if Q dot dot tracks Q des dot dot, right? Then you have them coherent. If it's not tracking properly, then you might have a difference. But this doesn't mean that at each state you try to linearize the system with the actual state. So the usage of Q and Q dot state are to linearize the system. Then the tracking will be at each loop responsibility of the tractor that is inside here. So you might have difference. And the new thing is that we enforce the dynamics as an equality constraint. So we have these accelerations that can do whatever they want. The torque can do whatever they want. We just do this, I try to minimize this error, but this, what links the accelerations to the torques is the dynamics. So if we find a solution for these variables, we are sure that they will be feasible, that will be respecting the dynamics of the robot. Here we are talking a fixed-base robot. We see the extension to floating base. In the case of task space or operational space inverse dynamics, we have the do a quick mapping. So we have the reference. Again, we write at acceleration level. We have the error in acceleration. Well, this is the reference we computed with the feed forward and virtual PD. And then, since our optimization variable are q dot dot and tau, I need always to, when I want to define a task in another variable, I need to find a relationship that links the x dot dot to the optimization variable. In this case, it's the well-known kinematic relationship. Again, this is measured, and we can find a relationship with q dot dot because we need to write a affine function of q dot dot or tau. So in this case, the affine function will be j q dot dot x plus j dot q dot minus q dot dot f. And how do we write our matrix? This will be the A matrix that we multiply for with 0, that we multiply for q dot dot tau, and then this will be the B matrix. So we try to minimize A, y minus B. Okay. And yeah, so again, subject to the same dynamic equation. These are least square problem because we have the true norm of the cost function.
So in both optimization, you're trying to find the torque, right?
The torque, yes.
And then by finding torque, is the problem is not to become like a nonlinear optimization problem because you have this mapping from torque to, because your cost function is at the acceleration joint level and your control input is at the torque level. So you have a nonlinear mapping from there to there.
Why?
To get the from, because you have the inertia multiplied by the
Okay.
q dot plus the positive torque, right?
Yeah, but the inertia is a parameter.
Yeah.
If it would be a nonlinear mapping if I have q as decision variable, but I have q dot dot as decision variable, and I provide q. I measure q, so I measure m. So it's a parameter.
Okay.
At each loop, I read m, and I have a linear relationship between
Like,
between q and tau. This is a linear constraint.
okay.
Okay, it's subtle, but it's very important to understand this. Because we didn't incorporate q in the optimization variable, we are able to write linear constraints in acceleration and torque.
So it would be a convex problem?
Yes. Yes, because it's a convex problem, because this is,
Yeah.
we say this a least square is a specific type of QP, wherever you have the two norm, the J matrix as well. J matrix is dependent on Q, but we said we measure Q, so we provide this. This is a parameter. It's like a set of numbers, and we optimize for Q dot dot. So this is a convex cost and a linear constraint in Q dot dot tau, and therefore this is a QP, is a convex problem. It can be solved with one step. No, not one step. It can be solved quite quickly.
And using a virtual control input, I mean, like if you linearize everything, would it be better for the optimizer or is it the same? Given that this is a convex problem already.
Linearize what?
Like you do instead of computing torque, you compute the virtual control, like you have the inverse of the inertia, and then you have one parameter that you are looking for. You get my point?
Well, you are in essence doing this is the same as doing what you say.
Mm-hmm. It's the same, right?
It's the same thing. It's like writing it explicitly in an optimization form.
Mm-hmm.
So it's exactly the same thing. You don't have to linearize anything because you express the tracking error at the acceleration level, and you enforce the dynamics.
But now if your cost function, instead of being at the joint acceleration, will be at the joint position, let's say, then we'll using a virtual control optimization would make the problem convex, or
Now, if you have the joint position, then it's becoming nonlinear because J depends on the joint position, M depends on the joint position, H depends on the joint position. That's what you don't want to do. People don't do that whenever they write a controller. They do in the optimization of trajectory because they need an horizon. So the characteristic of this kind of class of controller is that they are one shot, they are blind, they just look at the actual moment, here and now, they don't predict future. Okay. That's why they make that. If you want to consider an horizon, then of course it's not useful to have just acceleration. You need the position, the evolution of the system.
Okay.
So we consider fluid dynamic differently from before, where we had a quasi-static assumption. So this controller takes into account inertial coupling and can compensate for them. I saw this controller very good. For example, whenever we change our robot from IQ to IQ Real is a quadruped robot with legs that are very heavy, and their motion creates acceleration on the trunk that are very much higher than IQ Real because it's a fat leg, you know, it's full of stuff inside. And so this controller was able to behaving way better than the previous quasi-static QP because was taking into account this inertial effect and compensated for that. So it was cancelling, doing inverse dynamics, as you said, compensating this inertial effect. Till now we said we were talking about fixed base robot, but the extension to floating base, it's very simple. We just replace the dynamics with the floating base dynamics instead of a fixed base. So we have the selection matrix, and now we have 6 equations more. So this acceleration vector becomes n plus 6, and we have therefore 6 decision variables more. And since it's an optimization problem, now the good advantage, the big advantage for which we do all this complication is that we can add additional constraint for feasibility. So we can incorporate actuation constraints, we can incorporate kinematic constraints, we can incorporate velocity constraints, we can do whatever we want. Let's see what we can do. The feasibility constraint can be written as inequalities. The torque limits, if you have the torques as a decision variable, will be just bounds, straightforwardly implemented. If, as in IQ, you have a torque limit that is joint dependent, then you can compute the tau max function of the joint, because in the case of IQ you have a piston with a lever crank mechanism, so the lever will change and the force of the piston that is constant will map into a non-linear torque profile. And actually whenever it's retracted, the torque can drop very low, up to 80 Newton meter, while here maybe it's under 50. So this is quite important. and you can provide this just measuring.
the joint position. Then if you write acceleration level, again this is an optimization variable, and then you can write bounds of the accelerations. What about velocity? How do we incorporate velocity acceleration? So a trick is to assume constant acceleration between one sample and the other. So for example, we
Ricky, can you wait? Because they are saying that the volume is not so.
Sorry?
There is a lot of noise in the Teams team stuff.
Reduce the noise due to what? Ask people to remove their microphones.
No, they are new.
Mute all the microphones. So we can think about the velocity computed from the previous velocity, and therefore we can write this is the velocity. So think about the so if this is you have this constraint on velocity lower than q dot max, we should replace this expression in here, and then we have the previous velocity term. It's going here, and we have the acceleration q dot here. Same for the minus. And if you have acceleration, you do the same thing. You link, if you have position that are position limits, you do the same thing. You link the position to the acceleration, just with double integration. So this is the position after dt. This is the position of t plus dt q dot plus 1/2 dt squared q dot dot. So we take this as our matrix, A matrix or C matrix, constraint matrix q dot dot, and we put in a known term on the right, q max minus q minus dt q dot, with the same from the minus. This way the robot will start, when it gets close to the limit, will start to decelerate to avoid hitting the limit. Sometimes dt is too small, maybe you want to use 10 dt. This is a trick, such that you will feel the influence of the kinematic limit a little bit before. And what happens is that when it gets to the limit, it gets some acceleration in the opposite direction. It creates a torque that will result in an acceleration in the opposite direction. So you see that the link clamps. And normally this position limit, of course, are used for the swing task most of the time. They're also used for the other tasks, but the one that hits the limit in general is the swing leg. So this kind of QP based problems, they allow you also to incorporate easily a COM task and a swing task together without any problem. And the fact that the swing will move will have an effect, inertia on the trunk itself, and this will be taken into account because we have a single formulation for all of them. While before, in the quasi-static approach, normally we use a PD control just to track the swing, and the whole body controller has no knowledge of that. So in the case of IQ Real, if you move fast, you can have the stabilizing influence on the trunk due to the motion of the leg. Then we do the extension. Till now we didn't talk about contacts. So the extension of this QP inverse dynamics in contact needs to have k additional decision variable that are the contact forces that appear in the equation of a dynamic equation and the contact constraints. So you know that adding the forces to the dynamic equation is not enough because we also need to add the contact constraints. So we have n+6 equation here. We are a floating base case and k contact constraints. We are doing a rigid assumption here, and we write them explicitly. And we have, in addition to the acceleration and torques, also the contact forces. Still the regularization term, plus we put some regularization also on the acceleration and torques to bound the solution. So we are in total, we have n+6 plus k constraints, n+6 acceleration plus n torques plus k variables. So we can have some redundancy. Shaping the cost function, we can have, as before, different solution. With W, we minimize the true norm of the force vector. With this, we minimize, we try to have the forces in the middle of the cone. And with this, we try to minimize the torques. Something we didn't talk before is the compliant contact case, because till now we talk about the rigid assumption. And in the case of compliant terrain, let's say we want to model the contact as compliant, we need to add these additional constraints that relates the contact force to the penetration epsilon of the terrain. So we have terrain stiffness, terrain damping, and the force is the result of the penetration of a contact point below the surface. So whenever pz becomes negative and epsilon is positive. But I need to measure the penetration, so this is very bad because I need a very accurate state estimation. I need the forward kinematics to compute the foot position without any error, and I need to measure a penetration maybe of 1 or 2 centimeters, which is quite hard. So one approach, one idea that one of my students had is to add the penetration to the decision variable, to the set of decision variables, and link this penetration, in this case the acceleration of the penetration, which is the opposite of the position of the foot acceleration, that will not be zero. So we remove the stance constraint that we set before, and we replace with this, and we enforce the penetration to be positive. Also, f can be a nonlinear function, generic function of the penetration. In this case, you can emulate, for example, nonlinear stiffness, like for the foam or sand or different contact model. The problem that is then the optimization becomes nonlinear and so no longer QP. The problem formulation found by my student Fahmy, Shamel Fahmy, is that f is no longer a decision variable because it has its own dynamics defined by the compliance of the terrain. We have epsilon in place of f, so we replace directly f as the contact penetration times the stiffness plus the damping, and we link as we say, we need to link this to the joint accelerations the double derivative of the penetration, and but since we have the epsilon as a decision variable, we need to also express this double derivative using the previous measurements of the penetration. And we have the penetration to want to be positive, it cannot be negative, and there is no need to measure epsilon this way.
So this was the work done for Stans, right?
Yes, the paper is called Stans, and it was published this year in Chiaro. Okay, just a quick remark on the fact that you don't have to stick just to acceleration task. It could be whatever. It could be, for example, a force task. So an acceleration task is written this way, but it could be a force task if you have using the force variables. So you have different flavors. We will see here next how do we use them. And if we look at some computational aspects, we can state that the computational cost in a QP it's dominated by the computation of the Hessian. And the computation of the Hessian normally it's done. It involves then we will have to do a choreographic decomposition that is proportional to the nonlinear with the number of decision variables. As it grows with the cube of the number of decision variables, the computation time. So trying to speed up the QP, we should try as much as possible to reduce the number of decision variables. So is there something we can do here? What do we need all of them? Do we need all these decision variables? Knowing whatever you saw till now, do you think we need all of them? Or we can kick out some of them?
Q double dot maybe.
No, yeah.
Q double dot.
I suppose we don't look at all of these variables because some of them takes running others.
Yeah, so there is a link actually. We said that from two of them you can get one or the other one, no? Using the actuated dynamic equation. So we can exploit this to eliminate one of them. Let's say we want to. So if we exploit the sparsity structure of the floating base dynamics, we can split the actuated from the underactuated part, and we can let's say we can remove the torques, for example. So now we define a formulation of the QP problem we call the reduced problem, where we no longer have the torque as decision variable, but we have only the accelerations and the contact forces. Why this is possible? Because if you look at the dynamic equation, now here is missing the Jacobians, but you have the underactuated mu part, the inertia, let's say. No, sorry, the Jacobians are on this side because we have the forces here and the acceleration. And we see that you have the actuated inertia, and we want to express tau as an affine function of q dot dot and f.
Q dot
And
dot
this is
in this
possible.
case is both.
Huh?
Actuated and underactuated is Q dot.
This is actuated.
The
The blue one.
dimension of Q dot is n or n plus 6. Q double dot.
N plus 6.
We are considering
N plus 6 because you have the 6 part here and the n part here. So we have 6 equation here, underactuated part, and n equation, actuated part, and still we are still in the rigid contact situation. We have the k contact constraints that are the stance constraints. These are the feet that are in steps. So to solve this situation, the robot needs to know which feet are in stance to get a proper solution. So the torque can be used using this equation. The torque can be obtained from the acceleration and the contact forces. And so we can do a change of variable where we reduce the set of variables to just this one. And the reduced problem will look like this, where if we look here, we have only the underactuated equation and the contact, the stance constraints. We have only accelerations and forces as decision variable, and these are the Newtonian equation and here in the second of the contact. Plus, we have the friction cones as before. But we want to enforce the torque constraints. So what we do now? We do the same trick. We know that we can compute the torques from this equation. So we want to set the torque limits, but we don't have the torques as decision variable. Who cares? We use the define function to express the torques as function of the sorry, this is wrong. Yeah, this is it's both. It's B transpose J. J. And this is wrong as well. J transpose minus Hubert dot F plus Hj. Okay, so we have our mapping to the decision variable, and this is the V. So if we want to do tau minus tau max, we go A times Y lower than tau max minus this term. So I will correct this. Okay, so here the last step is whenever we solve for the acceleration and the force, we still use the same relationship to go back and compute the torque, the desired torque that we send to the low-level controller. So this way we reduce the dimension of the problem. We said that typical control frequency is 1 millisecond, 1 kilohertz, so 1 millisecond for the loop. The dimension of the problem before was n plus 6 plus n plus k, and now for the reduced one it's n plus 6 plus k. The equality constraints, we have the dynamics, the full floating base dynamics plus the contact. Now we have only the underactuated dynamics plus the contact in the reduced one, and the inequality constraints are always the same because we can still enforce them, and there are n for the position, for the kinematic limits, and for the velocity limits, and for the acceleration limits, and the cones we consider 4 for each leg, okay, in contact, where C is the number of each leg in contact, because we have the 4 half plane of the pyramid. In the case of humanoid, in this case you map generally the contact, the friction cones as 4 smaller cones on the edges, on forces on the edges of the foot, so you don't have to care about the moment, and you have 3D forces times 4. So if you have 2 feet, you have 24 constraints. Number of degrees of freedom is much higher than in a quadruped. It's almost 30 or 50, depends how many joints you consider. So you can have a very big number of variable and constraints to solve in just 1 millisecond. And I want to conclude with an example, a very practical one. We want our quadruped IQ to do a static walk. For this, we have one task that is track the central mass trajectory, and the second task to move the swinging foot. And since these tasks are not conflicting, there's no problem, right? Because I can move the body and I move the swing, and there's no conflict. In cases you have conflict between tasks, then you need to build up an infrastructure for the optimization with priorities. So you need to solve a cascade QP where you define different priority levels for each, where on each level you have a set of tasks that are not conflicting possibly, and the conflicting one are on different priorities. But this is not part of this course. Maybe I will do another one in the future. It's super interesting, also tricky. And if we look, go back to our problem, we have the quadruped that has 18 degrees of freedom. We use 6 degrees of freedom for the CM task. Let's say we have 3 feet on the ground. So, for example, in a case, 9 degrees of freedom of stance constraints are removed. 3 degrees of freedom are for the swing task, because we have one leg moving with a point foot, so we just need to define the position. So in total we have 9 plus 3, 12 plus 6, 18. And we have no kinematic redundancy left, everything defined, everything is fine. There is no undeterminacy. And as ingredient, we select the decision variable. Since we love ourselves, we decide to stick with a lower set of decision variable. We choose the reduced model on the acceleration and contact forces. Then we need to define a central mass task. Now the central mass, we said, can be written at the force level or at the acceleration level. At the force level, we let's say define a branch at the the first central mass task is 3-dimensional. So we have just Newton equation here, and we have the desired branch coming from our PD control, our tractor, let's say, operational space, and then we can define from the Newton equation we can work out the relationship between the actual branch and the decision variables. The decision variables are in this case, so this is to don't confuse you. So let's say I have this COM plus mg equal to sum of forces, and I decide I can try to control this, or I can try to control this, knowing that both of them have the same effect. So in this case, I'm controlling the branch. Okay, so the task at the force level, it's minimizing what we saw in the quasi-static case, the error between the desired branch that we want to realize our springiness behavior to track the trajectory, and the actual branch that is something times, in this case, we have no accelerations in this case, and we have only forces, so something times the forces. So and the forces, this is since they are summing up the forces, you can see this A matrix as equivalent of doing the sum, right? Because and then you don't have. Sorry, this is swapped because these are the accelerations, and the forces are the second variable. Minus mg because you have an affine relationship because you have sum of fi, which is a f minus mg. So in our cost function we have a, these are the decision variable, minus mg plus w. This is our and this is the the acceleration level is the output of our tractor. It will be an acceleration reference. It will be, and we want to track this time. We want to track the acceleration of the central mass. So we want to find a relationship between the acceleration of central mass and our decision variable. So we know that if you think about the acceleration, the central mass is an end effector. You can define the JCOM, the Jacobian of the central mass, given q dot, sorry, and in here we have remember q base dot and qj dot. So we will have an influence due to the motion of the joint on the central mass motion, and the influence of the base on the central mass. We saw this JCOM how it look like, plus the term j dot q dot JCOM. Yeah, this, if you remember, this is the way that we define JCOM. And then if we define the acceleration error for x dot dot COM desired, then we get JCOM q dot dot plus JCOM dot q dot minus XCOM dot ref, and this will be the matrix this time at the acceleration level times y, and this will be the new term. Yeah. Then we have the swing task, same thing, we can do at the acceleration level, define using the swing Jacobian, so the Jacobian on the swinging leg, the swinging foot, we do the same thing, the stance constraints for the legs that are in stance. In this case, we use the constraint Jacobian for all of them, and we have the acceleration to 0, so we have this equal to 0. We put them together, and since we have two tasks that will not be conflicting, actually we don't even need to put a weight for these two tasks, but we can still define a weighting matrix to select, in case of unfeasibility, which direction we prefer with respect to the other to be tracked. Then we have as constraints, the unrestricted constraints, and the swing task. This is the swing task. The swing task. So we can have the stance constraint as hard constraints here. I don't suggest to put the swing task as hard constraint, because you can have you always want to, whenever it's like there is a push or it's hitting an obstacle, you want to allow some violation of the task. Yeah, this is it. If you have any question. Okay, so the lecture part of the course is finished. We see now the lab, which is the best one. The lab is, in essence, a collection of exercises where there is like a Python script that launches a ROS simulation, a Gazebo simulation with ROS as publisher to publish the joint trajectory. So you run the Python code, it will launch Gazebo, not visually, because for the virtual machine we have problem with graphics, but as a server, like headless, without graphics. And we can visualize the robot on hard disk. So the robot is IQ, and the Python script, in essence, reads the data coming from Gazebo in terms of joints and contact forces, and compute the control, and then generate a trajectory, compute the control, and then send the data, the control, the desired torques and joint positions to a ROS controller. There is a node that runs and directly interfaces with Gazebo. So we have a machinery to design whatever controller and locomotion algorithm in a very simple way. And I show you how does it work. So the robot starts on the ground, and here you see that we are setting, generating a reference for the pitch motion, but also for the Z height. And these arrows are the contact forces, the green ones are the actual ones, and the blue ones are the F star coming from the whole body controller that are mapped to torques, and then these torques are sent to the ROS controller, to Gazebo. So, do you have any question? So the idea of the lab, is to generate again a sinusoidal trajectory for the robot trunk. We generate a reference for the Z direction with a certain frequency, and another one with a different frequency for the pitch direction. And the whole body controller needs to be able to track both of them. First, we implement a quasi-static projection-based controller. We design the controller for the base frame, not for the COM, controlling position and orientation of the base frame. And the first step, as we said, is to create a virtual impedance, and then design a virtual impedance to track the reference. We first design a virtual impedance with a feedback only operational space PD. So position orientation, and then we map it to torque with the equation I showed you before. You need to compute the JB transpose matrix, and then we see that the tracking is super bad. We need to add a gravity compensation to the wrench, and you need to add the gravity compensation since you are writing in the base rate in this form, as we show, and then you see that the motion will improve a lot, but you still have tracking errors during the transient, even though you are eliminating during the steady state. And then you can add a feed-forward term to the wrench using the inertia and the mass of the robot, and try to implement the controller at the center of mass, check the static stability, so create a motion, lateral motion that will make the robot fall whenever the central mass projection goes out of the polygon, and then implement the quippy version of the controller that we saw this morning at the beginning, with with unilateral constraints, and afterwards with the friction constraints. And then there are some nice experience. So now you can have a look to the code. Let's go quickly through the lab. The important thing is I would like to show you is that if you just do the you don't set a flag for the feed-forward wrench, for the gravity compensation, sorry, because if you look in the folder that is utils control routines, you see that the controller, the projection-based controller, has some flags here, which is ischio and control, the gravity compensation, and feed-forward. So if we don't set the gravity compensation and we run, we will see where is this? Sorry. This is what is happening if you don't provide a WG that I was telling you. So it's really the whole body controller itself with the virtual wrench that is set to 1000, 2000 Newton over meter is not able to control the height. So unless you stiffen it a lot, increase the gains a lot, the gains you can find them in the config file, and they are this. So it's 2000 and 1000 for the proportional. Unless you stiffen it up, it's good to provide a feed-forward. Sorry, a gravity compensation, which is the second flag, and you can see the behavior is much better. Still you have the tracking error, but the steady state error you see. This is the two sinusoids are capped on the same point. Then we can add the feed-forward term. We see that the improvement, the tracking improves. Oh, sorry. I'll switch off this. Start. switch off bar. This my mistake. And you see that the tracking close. If we want to implement a QP controller, then we need to provide the normal directions to the contact. In this case, they are all vertical, 001, 001, 001, 001 for the whole legs. The fmin, which is the minimum value of the force to have unilateral constraints. So we want the Z component to be positive, and then we have the friction coefficient that we set to 0.6. And we call the function QP controller, where we provide this stuff, and this time we have gravity compensation feed forward, and we see what's happening. Okay, and you will see that if you increase the speed, the frequency, while the projection-based controller will be falling over, while the QP controller will still able to cope with higher frequency. Then you can play around with the friction coefficient. You can plot, for example, the constraint violation, which is whenever the friction cones are getting hit from the contact forces, and that's it. There are you can find different regularization, try the different regularization. Unfortunately, I didn't have time to implement that. And these are the constraint violation. You violate the constraint when these values go to 1. So to achieve a violation, you should, in this case, reduce the values of the friction coefficient, because the forces, tangential motions are very, very limited. So you never hit limits. And yeah, I think this lab is very complete. I will update that, adding more features. But it's a good starting point to create motions for the center of mass, for the trunk, and you can start adding then the swing and using this low-level controller. We will see in the second part of the course in autumn that we implemented a trajectory optimization for the center of mass in the trunk, and we will close the loop using this controller such that the robot will be able to walk replanning every once in a while, providing the reference trajectory that now is just hard-coded sinusoid to the orbital controller. So the course is finished. Thank you very much. I want to thank also mainly Angelo for the precious help. It would not be possible to have the recording without him, and also in replacing me doing experiments while I was preparing the lecture. So he did a very great job. And I hope you enjoyed that. Everything was more or less clear. Sorry for the typos and some problems that there might have been in the slide, because it was the first time I was doing this course, and I hope you enjoyed it anyway. So the exam, I don't know if you received the notification, will be in the afternoon around 4:30 in this same room, and the ones that are connected online will receive the PDF of the questions with the description of what to do on the same folder where the slides are located, and they should submit the final version by the time it's written in the PDF by email to my personal email, IAT. And will be valid if they are, I receive the email inside the time is given. Okay? So have a good lunch.